Okay, hello. Welcome back to Calc 1. Today we want to look at another rule for taking derivatives, in particular the chain rule. Okay. So some preliminary remarks for kind of an intuitive understanding of what's going on here. Consider the following two functions, right? So f of x equals, let's say, 3x minus 2 raised to the second power versus f of x equaling x squared. Okay, we know how to take the derivative of the second one. F of x, f prime of x. What do? You bring down the exponent and to the front. It's just the power rule, right? And then subtract the old exponent by 1. So 2 minus 1 is just going to give us 1. Okay, so one option we have for this problem is to just FOIL it, right? For this other problem on the left, you can FOIL, so you get 9x squared minus 6x is minus 12x, then plus 4, and then take the derivative piece by piece, term by term, and you get 18x minus 12, okay? But we kind of want to approach it like this second problem here, okay? I just want to do a power rule somehow and see if I can make it work. So to take the derivative, what I'm speculating is I can do kind of a power rule idea. So bring down the 2 in front. I have 3x minus 2 now to the first power, and maybe that'll work, right? So if I distributed, would I get the same thing? Or maybe in the reverse, if I factored down below, would I get the same thing? I can factor out a 6 here, and I get x minus 3x minus 2, excuse me. And it looks pretty close, right? It's just it's off by a factor of 3. So is there any way to remedy this situation? And yeah, there is. It's the chain rule. And how do we remedy the situation then? Well, what we're going to do is take the derivative of this part, okay? So that's that factor of 3 that you would be missing with the derivative. Okay? So if you have them, let's kind of redo it. Let's take number 1 and see if we can actually get the right answer. I have f of x equals 3x minus 2 squared. I'm going to do a power rule on it. Okay, so I can bring down the 2. Then I'll have 3x minus 2. But I have to remember that sort of tack on the derivative of the insides. Okay, that's that factor that I was talking about missing. So the derivative of 3x minus 2 is 3. And then, you know, the associative or commutative law of multiplication, we can regroup this stuff and you just get, or if you'd rather, you can distribute, right? So you get the 6x minus 4 times 3, and then if you distribute the 3, you get the 18x minus 12, which is what we found to be the derivative the long way, right? Okay, so that's the chain rule. That's kind of the thinking. Let's make it a little more formal and rigorous here. So first, the chain rule. Okay. So if you have a composite function, so if y equals f of g of x, or maybe we could say f of u, and then let u be this g of x thing, then you can find the derivative of y with respect to x using our Leibniz notation. What will that be? That'll just be the derivative of y with respect to u times the derivative of u with respect to x. Or if you rather the other kind of notation, which maybe is easier to read, the derivative with respect to x of this composite function is going to be equal to the derivative of the composite, kind of the shell, the outer shell part of it, times the derivative of the inner shell, like this, okay? Okay. So let's go ahead and actually try some of these, I think. In the beginning of the book, what we'll try to do is kind of have you just identify the bits and the pieces, like here's the inside, here's the outside. That's, let me just show you one example of that. So kind of a decomposition process that we'll want you to do. Sorry, having a little trouble with my pen, as usual. So decomposition. They just want you to identify what is f of x and what is the inner part, g of x. So, for example, something like f of g of x equals 5x minus 8. Okay. So f of x, 5x minus 8 to the fourth. F of x, or if you'd rather, f of u is going to be u to the fourth. Okay. And then this u part, if you wish, is basically g of x. U will equal the inner part, so 5x minus 8. Okay. And the reason why they're doing it this way is because the next step then, to figure out the derivative of this guy, you could kind of just take the derivative of these things and then tack them all together, and that would be your answer. Okay. So for example, the derivative of f of u is going to be 4u cubed. And then the derivative of u, so let's just say, I guess u prime, would be 5. Okay. So your derivative of f of g of x, the derivative of this mess with respect to x, is going to be 4u cubed times 5. And of course we have to back substitute what is u. Well, it'll be 4 times 5x minus 8 cubed times 5. And then you could rewrite it as 20 times 5x minus 8 cubed, okay, for your final answer. Okay. So that's their motivation for doing that. Let's actually just, I just like to dive right in and start applying the chain rule right off the bat. So let's instead kind of go in that direction. So this is section 3, applying the chain rule. Okay, so let's look at one. So an example, we have f of t equaling 9t plus 2 to the 2/3. Okay, so if you want to play this game where you're kind of identifying the outer part and then the inner part, you would say the sort of the outer part, f of, I guess, u is equal to u to the 2/3, right? And then the inner part will say u is equal to 9t plus 2. So if you wanted to, you could just substitute this u expression into this u to the 2/3, and you'd end up with f of t, right? Okay, so to find the derivative, what we do is take the derivative of the parts here. So the derivative of f of t is going to be the derivative of f of u, okay, which is 2/3. U to the 2/3 minus 3/3 is minus 1/3. And then times the derivative of u, which is just 9. Okay. So at the end, we have to back sub, right? So you can't leave it in terms of u. 2/3 times 9, so 3 will go in the 9. 3 times, it'll give you 6 in the front. Let me erase that 2. So we'll have 6u is 9t plus 2. So I'm just subbing u in here. And then that's raised to the negative 1/3. If you want to get rid of the negative exponents, by all means, it'll be 6 all over 9t plus 2 to the 1/3, or you could use a cube root if you'd rather. Okay, let's look at another one. So another example, f of x equals the cube root of 12x minus 5. Okay, which you could rewrite as 12x minus 5 to the 1/3. Right? Okay, so the outer part, f of u is going to be u to the 1/3. And then the u is the 12x minus 5. Okay. So again, to get the derivative, we just take the derivative of the pieces. So the derivative of f of u will be 1/3 u to the 1/3 minus 1. So 1/3 minus 3/3 is minus 2/3 times the derivative of 12x minus 5, which will be 12. Okay, so 3 goes in the 12 times, so we're going to get 4u, and u is 12, I'm back subbing, 12x minus 5, to the negative 2/3. And then if you wish, you can get rid of that negative exponent. I won't penalize you on a test if you don't do that, but some people just hate those negative exponents. Okay, so there we go. Okay. So I just want to give you a bunch of examples here. Let's try another one. Y equals 4x minus 1 cubed. And for these kind of, once you get the hang of these simpler examples, it's not necessary to do the f of u and u thing. You can just kind of see how it works, right? So what we're doing is it's a power rule. You're bringing down the 3. Okay, so you'll have 3 times 4x minus 1. And then you multiply by the derivative of what my physics teacher at CSU called the guts. Okay, so it's the derivative of the outer part times the derivative of the guts. And the derivative of the guts in this case will just be 4. Okay. And of course, I forgot to subtract the exponent by 1. Okay, so this is out being 12 times 4x minus 1 squared. And of course, if you got to do it the long way, do it the long way. You know, you ain't got no choice then. So you could say, all right, y is u cubed, and then u is 4x minus 1. So y prime is 3u squared times the derivative of u, which is 4, which of course would be 12 times u, which is 4x minus 1 squared. Okay. Okay. The problem, the reason why you might not want to be doing this substitution thing is because when the problems get a little harder and they start throwing in quotient rules on top of everything, it becomes a little bit, I don't know, too much. Okay, to be having to do all these weird substitutions and stuff like that. So for the easy ones, I advise you to kind of just do, take the derivative of the outer part times the derivative of the guts. Okay, let's see another one like that. So y equals the cube root of 6x squared plus 1. Okay, you may want to rewrite it if you don't notice it. It's a power rule type deal. And so if you just go directly to the derivative, power rule, bring down the 1/3 times 6x squared plus 1 to the 1/3 minus 3/3, which is minus 2/3, times the derivative of the guts, which would be, in this case, 12x. Okay, simplify it. So 12 times 1/3 is 4. So we have 4x times 6x squared plus 1, so negative 2/3. And then we like to get rid of the negatives, usually the negative exponents again. So all over 6x squared plus 1 to the positive 2/3. Okay. But again, you could do it with the substitutions if you want. I'll show you that way as well. So y would be u to the 1/3, and then u would be the 6x squared plus 1. So y prime, you get 1/3. So 1/3 u, and then to the negative 2/3, and times the derivative of u. So that's going to be 12x in this case. So the derivative, sorry, I should be multiplying those together, is 1/3 u. We can go ahead and substitute that in then. 6x squared plus 1 to the negative 2/3 times 12x. And then, of course, simplify. 1/3 times 12 is 4. So you get 4x. Basically the same thing you got above. 6x squared plus 1 to the negative 2/3, which is this guy right here. Okay. All right. Let's get another one here. It's number 19. It used to be number 19. I'm just going to write it as an example. So what is it? X is 1 over x minus 3 squared. Rewrite it so you could take advantage of the power rule. So this would be the same as x minus 3 to the negative 1 raised to the second power, and then you can multiply the exponents, and you get x minus 3 to the negative 2. I guess the chain rule isn't even necessary here because the derivative of x minus 3 will just be 1. So kind of the shortcut way, do a power rule, so you bring down the negative 2, and you have x minus 3 to the negative 2 minus 1 is negative 3. And then multiply by the derivative of the guts. So the derivative of x minus 3 is just 1. Then make it look nice. So negative 2 all over x minus 3 cubed. Okay. All right. So that's kind of the idea. If you're going to do the sort of substitution way, that's fine. But like I said, later on, it becomes a little cumbersome when we start throwing in product rule and the quotient rule. And right now, that's what I'm going to do. I'm going to throw in the product rule and the quotient rule on top of everything. And you'll see, all right, this is getting more complicated, right? So anyways, f of x is x times 2x minus 5 cubed. Okay, and now you'll find the derivative of this thing. And of course, you're going to need a product rule. Okay, so f prime of x, you take the derivative, you leave x alone, right? So leave x alone, but then times the derivative of the 2x minus 5 cubed. So you do a power rule, 3 times 2x minus 5 squared, and then tack on the derivative of the guts. So the derivative of 2x minus 5 will just be 2. And then plus, now you leave the x alone. Now you take the derivative of x, which is 1, times the 2x minus 5 cubed. Okay. All right. So this would be 6x times 2x minus 5 squared plus 2x minus 5 cubed. Some books will have you simplify this. I mean, that answer is fine for me. Anyways, if you were mystified by this part right here, that's the part where I'm doing the chain rule. Okay. So if your function was just the y equals 2x, you may have to, if you're doing substitution, you may have to kind of do it in your margin, right? So your y is u cubed, and then your u is the guts, the 2x minus 5 part. Okay. I'm trying to remember my physics teacher's name at this point. I kind of forgetting everything. Was it not Wiley? It's I've forgotten his name. Oh well. Okay, so then you take the derivative of this, is y prime is 3u squared, times the derivative of u, which is just 2, and then of course that's 6 times 2x minus 5 squared, which is just that thing right there I put in the box. Okay, so if you need to, you kind of just do it in your margin. Like a long time ago, you'd probably have to do arithmetic in your margin. Now instead, you're doing little derivatives. Okay. All right. Let's look at another one. So quotient rule types. These become important later on. The square roots are important with distances and that sort of thing. So they pop up in a lot of mathematical modeling situations, and you have to deal with it. So something like this may come up quite often in like a Calc 3 class where you're trying to find what are they called, like these vectors that are unit normal vectors, so they kind of point in a perpendicular direction to travel. You'll have a unit tangent vector and a unit normal vector, and this will be something that results in those calculations. But anyways, you'll have to be able to take the derivative of it. Let's rewrite it a little bit. So you get x all over x squared plus 1 1/2. Okay. If you need to do some scratch work to the side, because you're going to need the derivative of the denominator when you go to your quotient rule, you can. So let's say y is that denominator, x squared plus 1 to the 1/2. And then do our you know, if you need to do your u thing, so y is u to the 1/2, and then u is x squared plus 1. So y prime will be 1/2 u to the negative 1/2 times 2x, and then back substituting and simplifying a little, you'll have x all over u to the positive 1/2, and of course u is x squared plus 1 to the positive 1/2, or square root. Okay. And depending on how much extra work you have to do in your margin, you know, I do some in my head, but that's what we need. Okay, so to get the derivative, we have to do the quotient rule. So low times the derivative of the high minus high times the derivative of the low. And I just sort of did the derivative of the low here. And actually, I'm going to leave it in terms of half power. Okay, let's get rid of that square root to the right in my scratch work. I'm going to rewrite it as a half power. Okay, so I'll have x times x all over x squared plus 1 to the 1/2. Okay, and then this is all over the denominator squared. And if you square square root, it'll go away, right? So you'll have x squared plus 1 to the first power. Okay. This is a complex fraction, and the numerator you see a fraction within the fraction, right? So let me clean it up a bit. So I'll have x squared plus 1 squared plus x squared all over the x squared plus 1 to the 1/2. This should be to the 1/2 power. I apologize. Right there. Okay, and then this is all over x squared plus 1. And you probably have a couple tools from algebra with regards to simplifying expressions like this. What I generally will do is multiply to get rid of that denominator in the numerator, that x squared plus 1 in the second term. Let me mark it in blue, I guess. It's this thing I want to get rid of. Okay, so to get rid of that thing, I'm going to multiply top and bottom of the fraction by that same thing. Okay, so x squared plus 1 to the 1/2 up top. But then if you multiply it in top, you have to multiply it on the bottom as well. Okay. So here I'm distributing, right? So x squared plus 1 to the 1/2 times x squared plus 1 to the 1/2 is x squared plus 1 to the 1. And then the second term, when you multiply those, the denominator will cancel with the factor it's being multiplied by, and you just be left with the numerator, which is x squared. And the denominator, you have like bases, and so all you do is add the exponents. So you have x squared plus 1 to the 1/2 plus 1, which is 3/2, and then combine like terms in the numerator, and everything should be hunky-dory. This should be a minus. I don't know why I magically turned that into a plus, but it should be a minus here and here. Okay, sorry about that. So at the end of the day, looks like we're ending up with just 1 all over x squared plus 1 to the 3/2. Okay. Okay. I always put a problem like this on the test, so I expect you to master it, this type of problem, and you'll be seeing it again. Okay. Okay. Let's look at maybe another one here. A couple more. So example, we have y equals x plus 5 all over x squared plus 2. And then this thing is squared. Okay. Okay, so for the chain rule on this guy, it's kind of like you can complete the outer part no problem, the y equals u squared, right? But that inner part is going to require a quotient rule. So it seems like you got a bit of work on your hands. So at least for y prime, it's just 2u, but for u prime, it's work. So low times the derivative of the high is just 1, minus the high times the derivative of the low, and in this case, the derivative of x squared is 2x, the derivative of 2 is just 0, and then all over x squared plus 2 squared. And then we simplify that stuff, so I get x squared plus 2. And then I have to distribute 2x and the negative part as well. So it would be minus 2x squared minus 10x. And then that's all over x squared plus 2 squared. Okay. So at the end, it looks like we're getting something not pretty. 2 minus 10x minus x squared all over x squared plus 2 squared. Okay, and then we just have to write it all out. So, for the derivative, it's y prime times u prime. So it's going to be 2 times u, and u was above x plus 5 all over x squared plus 2. And then times the derivative of u, which we just find to be 2 minus 10x minus x squared all over x squared plus 2 squared. And you could simplify this as you wish. This answer seems perfectly fine to me, but it seems like, well, these kind of guys are like the same base, so we can multiply those out. So I could go in the numerator, 2 times x plus 5 times 2 minus 10x minus x squared. And that would be all over, it seems like x squared plus 2 cubed. Okay. But the previous answer would be fine in my book. I don't see any reason for all the... Okay, let's move on. So some transcendental functions here. So here's 5 tan of 3x. Okay. The inside part is that 3x. Okay, so the outside part, if you will, is 5 tan of u. And so again, the inside part is the guts, is the 3x. Okay, so to get that derivative, then y prime is going to be 5 secant squared of u, and then u prime is just 3. So multiplying those together, g prime of x is going to be 5 secant squared of u times 3. And then you have to back sub and multiply out, so you get 15 secant squared of 3x. Okay. Let's look at another one. This one is a little more difficult because there's multiple compositions going on. Okay. So you can have you can take functions apart as much as you want, really. So for example, this guy, there's actually 3 parts to it. Right? There's this inner part, the 5x, and then the next level out would be tan of that 5x, and then the next level out after that would be the square of tan of 5x. Okay? So there's actually 3 parts to it. If you do the u subtype idea, you go y equals u squared, the outer part, and then u would be something like the tan of z, and then so you have to add in another variable to handle it, and then z would be something like the 3x part. And if you compose all 3 together, so y of u of z, you should get the tan squared 5x. Okay, so you're plugging in the 3x in for z and for u of z, okay? And then plugging in tan 3x into y would give you tan 3x squared. So you should be able to rebuild your original function if you compose all 3 of these. Okay. So let's go ahead and figure out what we got then. If you take the derivatives, g prime of x, the actual derivative is the derivative of u, which is 2u to the first power, times, the derivative of y, which is 2u to the first, times the derivative of this u expression, which is secant squared of z, times the derivative of the z expression, which is 3. Okay. Then putting stuff back together, we have to back substitute. We'll have 6 times u, and u is tan of z, times secant squared of z. And then back substitute in the z. So we'll have 6 tan of 3x times secant squared of 3x. And that would be your answer. Okay. Let's do another one like on that level with these three parts in it, right? So example, y equals sine of tan of 2x. Okay. So in this example, the outer part is sine of something, right? And then the something is tan of something. And then finally that something is 2x. Okay. So for the derivative, you just go straight across, take the derivative of this row of functions. So you'll end up with a cosine of u times secant squared of z times the derivative of z, which is 2. And rewriting that, back subbing in the u, I get 2 cosine of tan z times secant squared of z, and then back substitute in the z value, which is 2x. You end up with 2 cosine of 2x times secant squared of 2x. Okay? Okay. They can make them really difficult, and if you take like more of an honors calculus, maybe you'd have something like g of x equals the square root of 1 plus the square root of 1 plus the square root of 1 plus this. You keep on going as many as you wanted, but eventually x, and then having to find the derivative of that is considered fun. So if you want to challenge yourself, you can make up your own composite functions and really get in there. But most people don't have time, so you don't bother too much. But it's there if you want it. Anyways, the next section is on the logarithm, the derivative, and the natural log. And this thing, we'll just give you the definition here. So the derivative, the ln of x, is equal to 1 over x, and x is assumed to be greater than 0. In general, now that we have the chain rule, these definitions of derivatives are all going to kind of change, right? So instead of just saying derivative with respect to x, we're going to say the derivative with respect to some u function, which is probably in terms of x, right? So the ln of u equals 1 all over u times the derivative of u. Okay. So likewise, before, maybe we had introduced the derivative with respect to x of sine x. It's cosine x. But now the book, what you'll see in the book is because we have the chain rule, they're going to think of what's ever inside of sine x as kind of a composite function potentially. So its derivative now will be cosine of u times the derivative of u. Okay, so just something to watch out for. Let's work around with the derivative of the logarithm. So an example, we have y equals the ln of e to the x squared. Okay, so certainly we could kind of just use our properties of logs. This would be equivalent to saying x squared ln e, and then using the definition of the natural log, right? Natural log of e is equal to log base e of e. So you're asking e to what power equals e? It's just 1, right? So this is just x squared, and its derivative is 2x. Okay, that's not what the book wants, clearly. They want you to apply the chain rule with the derivatives logarithm rule. So here we go. So y equals the ln of something, and then z equals u, too many variables, u equals e to something else, and then finally that something else is x squared. Okay? So y prime, we know then, is the derivative of ln of u is 1 over u, and then times the derivative of u. Derivative of e to the z is just e to the z, and then the derivative of x squared is just 2x. Okay? And then we start back subbing. Let's put in u, so we have 1 all over e to the z times e to the z times 2x. Clearly, 1 over e to the z times e to the z is just 1, so you end up with the answer 2x, which is what they have here anyways. Okay. Dealing with absolute values. So another example. You may have seen this issue, f of x equaling ln of x squared. And then this is the same as 2 ln of absolute value of x. So why? It's so there's consistency in the domains. So if you look at the domain of ln of x squared, it's actually negative infinity to 0 union with 0 to infinity. Okay, so honestly, the domain of the natural log is 0 to infinity. So this is y equals ln x. Ln of x squared is a little bit different. Okay, it's going to be kind of everything on the other side as well. Let's go to the Desmos. Yeah, sure. Let's go to the Desmos and see what the ln of x squared looks like. Okay. Desmos, take a little break, right? Graphing calculator. So y equals ln of x squared. Oh, it looks like 2 natural logs, right? Not quite. Let's look at the ln, y equals ln of x. Okay, so the ln of x is not quite, this thing has been stretched. Let's look at the ln of absolute value x. Absolute value x. Okay, so the ln of absolute value x, and it's giving me an error. Use parentheses around the argument. Well, I want the absolute value. Okay, buddy. Let's see if they give me. Let's sure. Let's see if they want the absolute value x. Maybe they'll be happier now. It's still upset. Well, anyways, the ln of the absolute value x guy should be the same as ln x, but it's going to be itself plus the translated version of it about the y-axis. I don't know why it's being such a jerk. It never was like this, but let me try it again. It's still being a jerk about it. Okay. Well, thank you. Yeah, so anyways, y equals ln absolute value of x is just the same graph on the right, but on the left, there'll be another copy of it. Okay. So 2 ln absolute value of x is kind of just a stretched version of this thing right here, this y equals ln absolute value of x. And why do we write it with the absolute values? It's to maintain that the double-sided nature of the ln of x squared. It has that domain which is bigger than the domain of just the regular ln of x. Okay, so every once in a while you'll see that occurrence. What then is the ln of the absolute value of x in more detailed terms? Let's just clear that up real quick. This is a piecewise defined function. It's the ln of negative x if x is less than 0, and the ln of regular x if x is greater than 0. Okay. The derivative, we'll be interested in. How do I get the derivative of this thing? You just take the derivative of the pieces. Okay. So the ln of negative x would be 1 all over negative x times the derivative of negative x, which is negative 1, which will be 1 over x. And then the derivative of ln of x is just 1 over x. And the other part stays the same. And so this is just equal to then 1 over x, right? It's just we kind of have a different domain than we normally would have had. So if we look back at the domain of the derivative of the ln of x, it's 1 over x with x greater than 0. So the only difference when you included this absolute value, so if you have y equals the ln of the absolute value of x, you need to take its derivative. Visually, you're not going to see a difference, but there will be some difference in the domain. Okay, so in this case, the derivative is 1 over x, but we have a different kind of domain. Okay. So in general, what they'll probably tell you is when you're taking the derivative of something like, for example, ln of x squared, don't overthink it. Its derivative, f prime, if you're not worried about the domain or anything, is just going to be 2 times the derivative of the ln of x, which is 1 over x. Okay, so 2 over x. Let's look at one more example. I feel like I butchered that explanation, but hopefully it's okay. Y equals ln of the absolute value of sine of x. Okay, so I'm just kind of ignoring the fact that there's absolute values there and taking the derivative as I would normally. Okay, so it's going to be 1 all over u, in this case u is sine x, times the derivative of u, which is cosine x. Okay, so I'll end up with cosine x all over sine x, which of course is just tan x. Or rather cotan x, sorry. Okay. Cotan x. Let's look at one more. So another logarithm type problem. Take advantage of your log rules when you can. So that's the moral of this next example. You have the ln of x all over x squared plus 1. You do not want to have to do a chain rule with a quotient rule, right? So what you do instead is use the quotient rule for logarithms to turn this into a difference of logs, and then take the derivative of the pieces. Right? So the derivative of ln of x is 1 over x, minus the derivative of ln of x squared is 1 all over the guts, times the derivative of the guts, which is that. Okay? And then if you want to, you can make it look much more pretty, but I'm just going to leave it like this. Okay. Okay. Bases other than e, I guess, come up every once in a blue moon. So first off, log base a of x. How do I handle that? Well, you're going to use the change of base formula from pre-calculus to turn it into the ln of x all over the ln of a, okay? Which in other words is a constant multiple of the ln of x. Okay. So to take its derivative then, if this was y equals that y prime, you leave the constant in front alone, so you get 1 over ln of a, and then times the derivative of the natural log, which is 1 all over x. And they don't write the, when they multiply together a natural log and a variable, they'll put the variable in front so you don't accidentally think the variable is inside the natural log. Okay, so they'll write it x ln a, not ln a x. That looks, it doesn't look right. Okay, okay. Likewise, or I don't know, kind of likewise, if you have a base other than e for your exponential, you're going to turn that into base e using kind of our cancellation equations for exponentials. So a to the x is the same as e to the ln of a to the x, because the e and the ln cancels. And then you're going to rewrite this as e to the x ln a, and then take its derivative. Okay, so let's see how that works. I got y equals a to the x, which is e to the x ln of a, y prime. When you take the derivative of an exponential, you just get that exponential right back. And then by the chain rule, you have to take the derivative of the guts of the exponential. And the guts of the exponential are in the exponent here. Okay, so the derivative of that will just be ln a. If you didn't quite catch that, let's try maybe another explanation. We have e to the x ln of a, right? So y equals e to the u, and the u part is x ln a. So to get the derivative of e to the u is just e to the u, and then times the derivative of x ln a, which is just ln a. ln of a is just a constant. It's like 5. You know, the derivative of 5x is equal to 5. It's the same spiel here. And then we have the back sub. You get e to the x ln a times ln of a. So you're either tacking on an ln of a, or you're tacking on 1 over ln of a, if it's the natural logarithm or if it's the exponential with base e. Okay, so one last thing then, e to the x ln of a is just a to the x, right? So all you're essentially doing is, like I said, tacking on an ln of a. Okay, so for example, if you have y equals 3 to the x, the short answer, y prime, is going to be 3 to the x ln 3. Example, if you have y equals log base 5 of x, the short answer, y prime, is 1 all over x ln 5. Okay, so you're either tacking on a factor of ln of a, or you're dividing by the ln of a, depending on whether you're working with an exponential or a logarithm. That's kind of what I was trying to say. All right. Then if you have maybe a composition of functions, y equals 3 to the sine x, maybe. So what is going to happen there is that you have to tack on the derivative of sine. Okay, so you'll get y equals 3 to the sine x ln 3 times the derivative of sine, which is cosine x. Okay. And you probably want to rewrite that as 3 to the sine x cosine x ln 3. Okay. Okay. Thankfully, those don't come up very much. And usually when they do, I end up having to look them up in tables of derivatives or something. Let's look at one more example. Y equals 5 to the x squared minus 2. Okay. So y prime will be the same thing right back, 5x squared minus 2 times the ln of 5 times the derivative of the guts, the x squared minus 2 part. So that would be 2x. Okay. And you can rewrite it as 5 to the x squared minus 2 times 2x times the ln of 5. Okay. All right, I think that'll do it for now. We'll leave it there, and I'll see you next time. Thanks for watching.